on 8.1 to 8.2, column 14, part E.
Problem 14, part E.
And it's the series of n equals 1 to infinity, 7 and 7 to the power of n all over 7 to the power of n plus 4.
N plus 4.
N plus 4.
And the instructions are?
The following series of geometric series are summed of two geometric series. Determine whether each series converges or not. For the series which converge, each of the sum of the series for the series which diverges into the DIV.
Okay. So let's write out the first 2 or 3 terms. N plus 4 is the power on the bottom, n is the power on the top. Our first value of n is 1. So we get 7 to the 1 divided by 7 to the 5. When n is 2, I get 7 squared divided by 7 to the 6. When n is 3, I have 7 cubed divided by 7 to the 7. So is there a common multiplier that gets me from here to here, here to here, and so on? R is equal to 7 over 7. You're right, we're always multiplying by 7 over 7. You get the 7 squared, 7 cubed, and so on. And so R is 1. What happens to the series if R is 1? Diverges. So that means this is getting bigger, so it's going to go to infinity. Okay? Geometric series will only converge if R in absolute value is strictly smaller than 1. Okay? Is there another one? Yes, ma'am.
Number 2.
Okay.
It's 131 over 5. Plus 30 R2.
You said 31 over 5?
Over 5 to the power.
Oh, the 5 has the end. Gotcha. Gotcha. That makes a big difference. N is going to infinity. Okay, so let's do this term by term. For the 31 over 5 to the n, the only n appears in the denominator on a growing function. So what happens to 31 over 5n? Goes to 0. Okay, now the 30 here is a constant, so it stays put. Arctangent of something that continues to grow. Do you remember that arctangent had horizontal asymptote at pi over 2? So this is going to be 30 times pi over 2. So the overall limit looks like it's going to be 15 pi. What else? All right.
Given AK equals n parentheses 1 plus C over K. Instructions are for both of the following examples, establish a given series or sequence converted by divergence.
Okay. So the sequence is this one. And the series would be this one. Okay. So this is the sequence. This is the series. A sequence converges if it has any limit in the world. If it has a finite limit, the sequence converges. The series converges. We've got our tests. What tests do we have? P series, geometric series, integral test, test for divergence. Those are the four things, or telescoping. We got 5 things that we can look for. Partial sums is the telescoping one. So what I'm going to do is the sequence part, because it's pretty easy to take a limit. If this limit takes some steps, because it has that exponential indeterminate form. So let's first test the sequence. So first, the sequence converges if it has a limit. So we're going to take the limit as n goes to infinity of our general term. 1 plus 2 divided by k. What's 2 divided by k? I guess I better keep it with k's. K goes to infinity to the kth power. And I said this is going to take some steps because this particular expression as k goes to infinity behaves like 1 inside the parentheses to the infinity power. That's an exponential indeterminate form. And I know from experience that when something has an exponential indeterminate form, I've got to use a logarithm and then try to manipulate the expression to be either 0 over 0 or infinity over infinity, in which case I take from there by using L'Hopital's rule. So I'm going to pretend that this is equal to some number L, and then I'm going to take the natural log of both sides. So I left room to put it right here and right here. We chose a logarithm because it's the thing that pulls exponents and uses them as coefficients. So in my next line, I have the limit as k goes to infinity of k times the natural log of 1 plus 2 divided by k. And over here, I just have the natural log of my limit L. The point of using a logarithm is to bring that power down. But when you bring the power down, now I'm multiplying by something that is infinite. And then the logarithm is going to be the log of 1. Log of 1 is 0. So I have infinity times 0 at this step in the game. That's not a L'Hopital's form. What do I do to take it out of the infinity times 0 form? Divide by 1 over k. So now I write that as the limit as k goes to infinity. Keep the logarithm on the top. Multiplying by k is the same as dividing by 1 over k. So do a little algebra. And now it has the form of 0 divided by 0. 1 over k goes to 0, and inside here I have the log of 1, which is 0. So now I can use L'Hopital's rule. L'Hopital's rule applies here. So we take the derivative of the top and divide it by the derivative of the bottom. The derivative of the log of u is 1 over u times u prime. So I write my limit right here. As k goes to infinity, here's my 1 over u. U is the stuff I'm taking the log of. 1 plus 2 over k. Now I'm inside these parentheses taking the derivative of 1 plus 2 over k. That has a derivative of 0. I'm taking the derivative of 2 times k to the negative 1. And so I get negative 2k to the negative 2. Or negative 2 over k squared. That's the derivative of the top. Now I'm going to divide by the derivative of the bottom. Think of that as a k to the negative 1. So I'm going to get negative 1 k to the negative 2, or negative 1 over k squared. And that's equal to the natural log of L. But I have a common factor now. That negative 2 over k squared is divided by negative 1 over k squared. So the negatives will cancel, and so will the k squareds. And all I'm left out of this is 2. And we'll put the 2 right here. We're canceling, and canceling, we're going to get 2. Now it's your turn. What's the limit of 2 over 1 plus 2 over k? 2. So 2 is equal to the natural log of L. But we want L. So I'm peeling off a logarithm with an exponential function. So we just found that the sequence has a limit of e squared. Our sequence goes to e squared. Well, that's telling me something. I have a series where the general term goes to e squared. So what happens to the series? It diverges because the limit of the kth term is not 0. The series diverges by the test for divergence. It's going to get infinitely large. Okay. Let me give you one similar to that, similar but easier. So here's my own example. Let's take a sequence that looks like 5, 6 to the n. And let's take the series that has that as its general term. Let's start my counter at n is equal to 1. And I want to know, does the sequence converge? If so, to what? Does the series converge? If so, to what? So start with the sequence. Take the limit as n goes to infinity of 5, 6 all to the n. What is that limit?
0.
0. So the sequence goes to 0. The sequence converges to 0. So now I can't apply the test for divergence. In my series, the general term does have a limit to 0. But remember, that's a test for divergence and not a test for convergence. I got to try something else. If the nth term goes to 0, proceed to a new test. Do you suggest any tests here? Almost. It's not a p-series. We could integrate it, but it'd be a little bugger. It's easier than that. It's a geometric series. Let's write out the first few terms. It looks like 5, 6 to the first power, 5, 6 squared, 5, 6 cubed, right? I'm proceeding by multiplying each term by 5, 6. This is a geometric series with r is equal to 5, 6. What's our conclusion on that? Converges, but not to 5, 6.
It's 5, 6 over 1.
Right. Our r is smaller than 1, so I know it converges. It converges to, the formula tells me a over 1 minus r. A is the first term. So in this case, A is 5/6 and so is R. So I have 5/6 divided by 1 minus 5/6, which is 5/6 divided by 1/6. Flip and multiply, and you get that the series converges to 5. Okay? So the general term going to not 0 tells you that this thing diverges. The general term goes to 0 tells you nothing. You got to try something else. Okay? So remember our test we had, our tests so far. We ask ourselves, the first thing you should always check, do the test for divergence. If the AK terms do not go to 0, then the series diverges. If the terms do go to 0, you try something else. You look for a P series. P series looks like 1 over K to the P power. P is a fixed number, K is the counter. And this converges for what size P? Greater than or equal to 1. Nope, not equal to, greater than 1. Diverges is equal to 1. Converges only if P is bigger than 1. We had the geometric series. Those can typically be written so that they look like A times R to the K power. And I can either start K at 0 or infinity. If I start at 0, then it's R to the K. If I start at K as 1, then it's R to the K minus 1. Either way, A is the first term, R is the multiplier. It converges for the values of R and absolute values smaller than 1. To the sum A over 1 minus R. Then we had an integral test. Positive term series, that if we can take that general term and integrate it as a function of x, that is a continuous decreasing function, the series does whatever the integral does. So I'm going to write AK as a function of x. Write it as a function of x in here and integrate it. The series does what the integral does. And then if we have none of these tests apply, the only other thing we have is to look at the sequence of partial sums. If the sequence Sn, which is just the sum from k is equal to 1 to n of the AK terms, if the sequence of partial sums has a limit, then the series converges to that limit. But writing that sequence of partial sums really depended on whether or not the series itself was telescoping. So usually works if the series is telescoping. Let me write a few up here and see what you know about them. I'll just stick another one in here. Okay, so let me put one up here. Converge or diverge and explain. Take the sum from k is equal to 2 to infinity of k divided by the natural log of k. So I kind of wrote the tests in the order that maybe you should try them. We'll take that lead. Somebody knows it, you're just not saying it. Diverge because?
Because if you take it as a series,
No, the limit's not 0. The limit's not 0. What's our tower of power? Yeah, this is a slower grower than this is. So it's a top-heavy function in terms of the rate of growth. That means it's going to go to infinity as k goes to infinity. So the limit as k goes to infinity of k divided by the natural log of k is infinity. So this diverges by the test for divergence. Right? Diverges by the test for divergence. Because the log of k grows slower than k. But if you did L'Hopital's rule, you'd see that. It has the form of 0 over 0. The derivative of the top is 1. The derivative of the bottom is 1 over k. 1 divided by 1 over k flips and multiplies and gives you k. As k goes to infinity, k goes to infinity. Right? So that's the test for divergence. If I flip it upside down, now it has a limit of 0, so I can't apply the test for divergence. It's not a P series because I don't have a power anywhere. It's not a geometric series because both the numerator and the denominator don't have a power of K. So we're going to try an integral test. So let's see if you can integrate the natural log of x over x. You're going to integrate from 2 to infinity, the natural log of x over x dx. Let me know what you decide once you've integrated it. Again? Hold on, hold. Again, please. Right. Right. So this is an n. I'm going to take the limit as n goes to infinity. This is infinite. And so your conclusion is? What's your conclusion about the series? Diverges by the integral test. What's different about that one than say natural log of k divided by k cubed? I made the denominator grow even faster, so that means the limit does go to 0. So we don't know much about the series. We need to try a test. And it's got a logarithm and a k to a power, so I'm going for an integral test again. So let's try the integral test again. Let's take u to be the natural log of x. dv, then I'm going to have a dv, won't I? Because I've got a k cubed now instead of, I'm integrating x to the negative 3 natural log of x dx. So do some version of a double substitution.
Yeah.
All right, let's take that as an x to the negative 2. Do that here and try double substitution. Okay, so u is the natural log of x, du is 1 over x dx. But then x is what? E to the u. And so if I write all this in terms, I would have, let's see what that looks like. Can I do it? That's e to the u to the negative 2 power. And then that's a u, and that's a du. That's still an integration by parts. So I'm not getting away from integration by parts. So let's go ahead and leave it at the original integral and do integration by parts with it. That was a nice try, though. So the integrand has to be decreasing. Do we know that the natural log of x over x cubed is strictly decreasing? Calculus 1, we were able to show a function was decreasing by doing what? taking the derivative and showing that it's negative. So I'm going to take a little time out here and convince you that I do have a decreasing function by showing you that its derivative at least is eventually strictly negative. So I know it's positive because I'm starting my counter at 2. So to show that f is decreasing, where f is natural log of x over x cubed, I'm going to take the derivative here and show you that it's negative. We'll do the quotient rule on that stuff. F prime is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And so I can simplify my numerator as x squared minus 3x squared natural log of x all over x to the 6th. And I've got a common factor of x squared everywhere. I'm going to take one of those out. I cancel x squared everywhere. I have 1 minus 3 natural log of x divided by x to the 4th. So I do have a critical number. Can you tell me the value of x that makes the numerator equal to 0? E to the 1/3. But let's see what happens beyond e to the 1/3. I don't care what happens before. My counter starts at 2, and then I have e to the 1/3. Well, that's the cube root of e. I bet it's a little bit bigger than 2. So let's put that here. And I want the sign of the first derivative. My denominator is always positive because it's to the 4th power. So I want to pick something bigger than e to the 1/3 and test it for my function here. E to the 1 is, well, e to the 1/3 may not even be in here, right? Because e to the 1 is 2.7. E to the 1/3, I don't know if it's in here, but e to the, I don't know. How big is e to the 1/3? Do we have a calculator? It's going to be smaller than e, right? So e is out here, 2.7. Let's use e as our test point. I put e here. What's the natural log of e? 1. So I have 1 minus 3. It's negative. And so I do have a decreasing function. I don't care about that little interval in between. For in the long run, it's a decreasing function. So now I can use the integral test. And I'm going to integrate by parts. I'm going to take u to be the log of x and dv to be x to the negative 3. So that du is 1 over x, d is x to the negative 2 over negative 2. And we're integrating from 2 to infinity. So I'll worry about the bounds after I compute the antiderivative. I'll write that as a limit. So the first part of my antiderivative is uv, and then I got to figure out the integral of v du. Here's my uv minus the integral of v times du. So I'm going to take this negative 2 out as a factor of negative 1/2. Make that a positive 1/2 out here. Inside here, I've got another x to the negative 1/3. X to the negative 3. This is going to be 1 over 2x squared times the natural log of x plus 1/2 integral of x to the negative 3 dx. Which gives me another x to the negative 2 over negative 2. extra negative sign come from? Yeah, I don't have it, do I? Right. I got too many negative signs, so let's put one of them back. Thank you. Minus the natural log of 2 over 2x squared plus 1/2 of x to the negative 2 over negative 2. So I'm going to make that a negative 1/4 and put that x squared down there on the bottom. So I'm going to have minus the natural log of x over 2x squared minus 1/4 and put that x squared down there. And so I'm going to get a common denominator here. I'm going to write that as a single fraction before I try to take the limit. So I'm going to multiply that first fraction by 2 over 2. And so I have minus 2 times the natural log of x minus 1, all divided by 4x squared. And we're to evaluate this from 2 to infinity, and then take the limit, say as n goes to infinity. And so I'm going to put an n here instead. Did I lose anybody in that simplifying? I lost myself. I got all confused up here. Didn't that common denominator and add and all. Okay, so an n is in there. I have minus 2 natural log of n minus 1 over 4n squared. When I subtract, minus 2 natural log of 2 minus 1 over 16. Does that limit exist or not? Well, which one grows faster? The denominator grows faster. So if we did L'Hopital's rule, one time, I should get that that first limit is 0, right? Because this will give me a 1 over n, and this will give me an 8n. The 1 over n will go down there and join the 8n. So I have a constant divided by n to a power. And so this goes to 0. This is a constant. So the integral is finite. So the series converges by the integral test. So I want to generalize the steps that we just did. Take this power off and put just a variable there as a fixed power. Let's use a q. What values of q are needed for this integral test to give me a convergent series? Consider the series from k is equal to 2 to infinity of the natural log of k divided by k to the q power. For what values of q will this integral test give me a similar result? Is that you that said that, Jeremy? Why do you think it has to be greater than 1?
Because when we tried that with K over just
Right?
so
when q was 1, it diverged. When q was 3, it converged. 1 has been a magic number for us. You see that when k is 2, all the same steps kind of hold. The only thing is I'd have an x to the negative 2 here. What we're needing is that we get this x in the denominator after we do the quotient rule. If this were a square root of x, if the k was a half power, and this is a negative 1/2, then it's going to end up in the numerator. So this particular series can always be integrated by parts, And that integral is going to converge only when k is strictly larger than 1. So it behaves very similarly to the p series, 1 over k to the p power, which converges when p is greater than 1. This series has a name. It's called the Q log series. This is a Q log series. And it's very similar to a P series. It converges for Q strictly bigger than 1, diverges elsewhere. Okay? Okay, so that's what we have so far. Test for divergence, integral test, P series, geometric series, and now a Q log series. And then we're going to add the comparison tests after you have a little break. I need a break too. Sorry? I can't hear you. You can stay in the room, yeah, oh, you can stay in the room. This is the day we usually move, right? Yeah, I don't want to sit that damn camera up again. Let's stay here. Let me see if they will make me run out. You never know. I don't remember when we moved in when we go. March or something? We are moving. There's people out there. Yeah, look at y'all. Look at them here.
No, hold on, wait a minute. Whoa. Hey, we just see the driver. Our class. Our class was good. Bro, we're still alone. We're still solo.
Okay, you guys, I gotta log off here and we're in group rooms and I'll log back on in a minute. So take a break.